Hello everyone. Today I'm going to present the topic two-dimensional viewing, which is one of the fundamental concepts in computer graphics. Whenever we display any graphical object on a computer screen, we don't see display we don't display the entire virtual world. Instead, we select only the required portion and display it within a specified area on the screen. This entire process is called two-dimensional viewing. In this presentation, I will explain the concepts of world coordinates, Windows viewports, viewing coordinate system, viewing transformations, window to viewport mapping, and the common viewing functions used in computer graphics. Let's begin with understanding what two-dimensional viewing actually means. Imagine drawing an entire city on a very large map. If you want to look at only one street, you don't need to see the whole map. Instead, you just focus on only the required section, right? So, computer graphics work in exactly the same way. The complete scene is defined in what is called the word coordinate system, where every object has its own position and dimensions. However, users actually don't want to usually display the entire scene. They only need a particular region. Therefore, we select a rectangular portion called the window. After the selecting window, this selected part is displayed on the screen inside another rectangle called viewport. The complete sequence of operations is known as the viewing pipeline, and the viewing pipeline consists of three important stages. First, the objects are created in the world coordinates, and then this the required viewing window is selected. And the third step is finally that the selected region is transformed and displayed on the screen. This process improves efficiency because the computer processes only the visible part instead of rendering the entire scene. Now, before moving further, let us understand three important terms. The first one is world coordinate system. This is the coordinate system where all the graphical objects are originally created. It can be thought of as an imaginary drawing space where designers create the complete scene. And the second term is window. As we have already discussed, a window is a rectangular region selected from the world coordinates. It defines exactly what portion of the scene we want to display. Anything outside the window is ignored during viewing. And let's move on to the third term, which is viewport. A viewport is the rectangular area on the display where the selected window is finally shown. One important point to remember is that the window exists in world coordinates, whereas the viewport exists in device or screen coordinates. So, in simple words, we can say that the window decides what to display and the viewport decides where to display it on the screen, like which part on the screen the image has to be like displayed. This distinction is very important in computer graphics. To understand this, we'll further move on to the next slides. Yeah. So now let's understand the viewing coordinate reference frame. So before mapping, you often move from world coordinates to a viewing coordinate system, right? Which will which will help us to determine if the window is rotated or not aligned with the axis. So we have to follow some steps, and that is called viewing coordinate reference frame. Also, sometimes the viewing window is not perfectly aligned with the x and y axis, like it may be rotated or positioned differently, right? So if we directly perform mapping, the calculations become complicated. And to simplify this process, we introduced the another coordinate system called viewing coordinate system. Earlier we were studying about the world coordinate system. So let's understand the steps here. The first step is to move the origin of the viewing window to the origin of the coordinate system. This operation is called translation. And let's move on to the next step. The next step is, if the viewing window is rotated, we rotate the coordinate system so that its axis align with the window. So yeah, the viewing window axis and the viewing window axis and the world coordinate window axis should be aligned uh, in the same axis. This operation is called rotation. After performing translation and rotation, all the objects are represented in the viewing coordinate system. Now, the mapping from window to viewport becomes much simpler because everything is properly aligned. And this intermediate coordinate system makes graphical transformations easier, more accurate, and computationally efficient. Now, let's move on to the next slide. Now, let us see how the transformation from world coordinates to viewing coordinates is performed mathematically. This transformation consists of two basic operations. The first operation is translation. As we have already studied, translation is the term which shifts the viewing origin to the world origin, right? And the second operation is rotation. Now, what is rotation? This also we have studied earlier in the earlier slides. Rotation aligns the axis of the viewing coordinate system with the world coordinate system. Instead of applying this transformation separately, computer graphics combines them into a single composite transformation matrix, which is represented by T. The translation matrix, which we have defined now, is represented by T, and the rotation matrix is represented by R. If we want to combine these two matrices, we have to multiply these matrices, right? So by multiplying these matrices, we obtain one transformation matrix that converts every point from the world coordinate into the viewing coordinate system. So instead of using two matrices, we are using now we are using one composite matrix, and it improves efficiency because every object needs only one matrix multiplication instead of multiple transformations. And this concept is widely used in computer graphics, CAD software, AutoCAD that is, and gaming, animation, and simulation systems. Now let's move to the next slide, which is window to viewport coordinate transformation. So yeah, there are some steps that we have to follow to convert the window coordinates to viewport coordinate. And for this transformation, these steps are to be followed. After converting the objects into viewing coordinates, the next step is mapping the selected window onto the viewport. And this process is called window to viewport coordinate transformation. Here, the size of the window and the size of the viewport are usually different. Therefore, scaling is required. Scaling is a new term for us right now. Scaling means to resize any image. We can like zoom in or zoom out, right? So that the image would be seen larger, and we can also make it smaller. So that is scaling. For let's take one example. For example, suppose our window has dimensions from 0 to 100, while the viewport occupies only 400 pixels on the screen. Okay, then the system calculates scaling factors in both the x and y directions, and after that, every point inside the window is converted proportionally into the viewport, which will ensure that the shape of the object remains same. The shapes should be the same, but the sizes could be differ. That is what scaling is, as I explained earlier. Only its size and position changes according to the viewport dimensions. And this mapping is extremely important because it allows the same graphical scene to be displayed correctly on different monitors and display resolutions. Now let us understand it with the diagram. So yeah, on the left side, we can see the window represents the selected portion of the world coordinates, right? And on the right, we have the viewport, which is the display area on the screen. The arrow indicates how every point inside the window is transformed into corresponding points inside the viewport window. Although the physical sizes of the window and the viewport are different, their relative positions remain unchanged. For example, if we take if an object appears at the center of the window, it will also appear at the center of the viewport after mapping. Similarly, the objects near the edges remain near the edges only. This proportional mapping preserves the overall appearance of the graphical scene. Without this transformation, objects would appear distorted and or incorrectly positioned on the display, which is not an efficient way to convert the window coordinates to the viewport coordinate. So yeah, finally, let us discuss the important viewing functions provided by PHIGS, which stands for Programmer's Hierarchical Interactive Graphics System. Let's start with the first function, which is evaluate view orientation matrix. This function creates the transformation matrix from world coordinates to viewing coordinates using the viewing origin and the view up vector. And the second function is evaluate view mapping matrix. This performs the transformation from the window to the viewport using the window limits and viewport limits. The third function is set view representation. It stores the view orientation matrix, mapping matrix, and clipping limits for later use. And the fourth function is set view index. It selects a particular viewing transformation whenever multiple viewing configurations are available. And finally, Set workstation window and set workstation viewport perform the final mapping between the graphic system and the actual display device. And these functions together complete the entire viewing process from world coordinates to the final image displayed on the screen. To conclude, two-dimensional viewing is an essential concept in computer graphics and that controls how graphical objects are displayed on the screen. We learned that objects are first created in the world coordinates, then a window is selected, transformed into viewing coordinates, mapped to a viewport, and finally displayed on the screen. We also have understood some of the definitions and some of the functions. So these concepts form the foundation of the foundation for many advanced topics in computer graphics. So thank you for listening.